recall everything I did yesterday, but I do want to recall some of the setting, because I want to save myself some time and not write the definition exactly, but just switch one letter from R to F. So just a quick reminder, X throughout the talk will be a pure, simplicial complex, chamber complex even. So you can think of it as just like I only deal with finite portions of buildings, or finite spherical buildings. Maybe someplace I'll take the complete complex, but nothing more. And we, for any such complex, we associated the vector space, the real vector space, space of R value I cochains. Chains, cochains, they are the same. Let's call them cochain. I will talk this exclusively. Cohomology. And we had coboundary operators. And a natural question would be, why are we just looking at R? What's so special about the coefficient ring of the real numbers? And the answer is nothing. This setting works perfectly well. The same definition applies for any field. Same definition from before will just will make sense. This holds for any field.
There is one more copy of R.
There is one more copy. Yes, thank you. This is for any field. You can even be more ambitious and ring, and if you're really ambitious, you can go to, if you really want to find interesting mathematics, then you should take here something non-commutative, but then you realize you have problems in high dimensions. Dimension bigger than 2, it's very hard to do everything easily. So in any case, let's stick for a field. And the two fields that we really care about are R, which we did yesterday, and F2, which will be my focus today, but F2 could be replaced by any other finite field. There is a price to pay though. For R, we had an inner product structure, and that enabled us to go to the eigenvalues and spectrum of operators. But if we are working in the setting of finite fields, we no longer have an inner product. What we do have is a norm this is really an R. And the norm would be defined similarly to how we define the inner product, but now we just take, there is no meaning to evaluate, like evaluating f at a specific cell won't give me a real number, so I will just think of it as a 0-1 case. If the f of sigma is anything but 0, then I give it 1, and otherwise I give it 0, and that's, so the norm is just counting the number of faces in the support of the cochain. And note that in the case of the field of two elements, cochains and subsets are interchangeably. Any cochain is basically an indicator function of a subset, and any subset is give me a cochain. This is okay. So using this norm and the definition from before, I can now give you the first definition. Sorry, now give you a general definition Okay, so for I smaller than d, theta equal than 0, denote the I-dimensional F coboundary expansion constant to be I'll denote it by H, and I'll put a little b here for reason to be clear shortly. What you get, this is a generalization of the Cheeger constant, but maybe I also need to put here f, but I'll probably stop mentioning the f. The f will be fixed throughout the discussion. So you minimize, just like in the graph case, you want to run over the coboundaries, the cochains, the I-dimensional cochains, and you want to look at the ratio, the co-isoperimetric ratio between the sizes of the coboundaries, but you want to minimize among all the different choices that give you the same coboundary. Well, this is what you really want, but as a first step, let's try and look at the following candidate. So, in the denominator, you're minimizing the sizes of all your cochain F and any addition of a coboundary. And why does it make sense to minimize over this? Because if you take the coboundary of F plus B, you get the coboundary of F. So F plus B has the same coboundary as F, and so it doesn't make sense to maybe F is not the right one, it's not the right filling of delta F. Okay, this is a bit abstract at first sight. And now, by the way, call x and epsilon or an F coboundary epsilon expander if this is greater or equal than epsilon for any I smaller than d. And let's see that, let's spell this definition, technical definition, in the case of dimension 1 for graphs. So dimension 1, and so I must, the only interesting case is I equals 0. Okay, so as I told you, any 0 cochain, and also for the field with 2 elements. Yeah, d equal 1, I equal 0, the field of 2 elements. So any 0 cochain will just give me a function on the vertices, from the vertices to F2, and I can just take the support, so I get a subset. I will let you check that the coboundary using this fancy language of cohomology is exactly give you the edges in the graph with one vertex in A. Exactly the edges that with one vertex inside A and one vertex outside of A. And for here there is something I haven't mentioned, but I'm also allowing the empty cell to be at minus one dimensional phase. And so B0 is the image of the coboundary on the minus one dimensional faces, which is just the empty cell, and that coboundary of the empty cell just gives me the constant function on the graph. So I get here 0 and the constant function of the graph. And note that f plus the constant function of the graph, and because we're working in F2, this is just, or I can look at the support of f plus the constant function, and this is just give me the complement of A. And so what we get is that HB0 of a graph over F2 is just the minimum running over all the subset of vertices which are not the empty set or everything, and you minimize over the size of A and the size of the complement of A, because both of them has the same coboundary, which is the usual graph Cheeger constant.
What does it give with R?
Sorry?
What does it give with R, the field? You take R instead of the field.
If I take R,
Yes.
thank you, that's a good question. Another remark. And now I won't just do it for dimension, for the smallest dimension, I can do it in all dimensions to see that it extends the same definition that we saw yesterday. So if f is equal to R, okay, so H, B, I, X, R is you minimize over all the functions in CI which are not in BI, and you're minimizing delta of F over the minimum of F plus B for any B in BI. And now I'm going to use the fact that I have an inner product, and I can use Pythagoras' theorem to tell me that for any function, any choice of function, there is one which minimizes this term, and that's exactly the function which is orthogonal to BI. Right? Those will be the functions where I decrease this the most. So I could just as well write, I could minimize running now only on the orthogonal complement and here I'm using inner product.
Sorry, what is the subscript is B on H? Yeah, right.
Yeah, it's B.
Stands for what?
It's B, like the story is that this is the coboundary definition. B stands for coboundary because I don't want to remember co, because there are many co. There will be cocycle and cosystolic, so I need the next letter which makes sense. And I want to say that the coboundary expansion is a definition, but it's not. There are issues with it, so I'll need to make a more refined definition, and it will be with a different letter. But for now, maybe when I write something small, you can just ignore it. It's, yeah. Okay. So, but
Shai,
yeah.
what's the reason for? So you've done this before in a previous talk as well, like this weighted sum with the degree, but it's not necessary for the but it's not necessary for the Cheeger constant. If you just put 1, if it's in the support, then you still recover the usual Cheeger constant in this case, right?
True. So here, the graphs that we consider were regular graphs.
Mm-hmm.
And when we're dealing with regular, there are no completely regular complexes. Or like finite quotient Bruhat-Tits buildings are not completely regular. Not every edge is containing the same number of triangles. There are some edges with different regularity, and that's fine. You want to, if everything was completely regular, you can ignore this. But because there is some difference in regularity between different colored faces in different dimensions, this weight function was introduced by Garland, and it looks superfluous, and you think you can ignore it, but it actually makes your life easy when you're trying to do induction arguments of expansion between dimensions. So this important, as was introduced by Garland. And there is a natural question whether anything I will say today, anything I said yesterday about the proofs of the Garland's method and the proofs of what I discussed today about coboundary expansion, whether it will hold if you remove this weight function. It makes sense. Like it shouldn't make much difference if we are in a bounded degree complex. It's a good question. I don't know the answer. Yes?
In your example, D is 1.
Here?
No, in the example.
D is 1. This example is just for graphs. Just spelling out this high dimensional cohomological language definition in the case of graphs. To see that we are extending the notion of expander graphs to higher dimension. Okay, and here so now let me just remind you, or maybe just notice again, using now the fact that even the norm, okay, so now I'm, so now I am slightly cheating, so now the cheat is that for the following step to work, I really need to replace the norm, let's call it the Hamming norm. With the natural norm associated in the real case. Now it does make sense not just to give 1 or 0, but actually to use actual evaluation. Okay, so there is a small cheat here. And modulo this remark, let me just say that okay, so let me emphasize what's going on. The whole definition of coboundary expansion requires, and the whole definition of cohomological expansion requires a complex from which you define requires a complex and some field of coefficients. So this enables you to define the space of f-valued cochains and the coboundary operator. You can define cohomology. But to define expansion, you need to specify how you measure cochains. So you need to insert a norm. And in this remark, in the real case, using the natural norm associated to the inner product, I can tell you that the coboundary expansion is equal to what we call the I-dimensional spectral gap. So there is a relation between this definition and the definition of a spectral gap, but you need to change the norm to the more natural norm in the real case. Okay. Yeah, so we see a dichotomy between the F2 case and the R case. In one of them we use the Hamming norm, in the other one we use the norm coming from the inner product.
Are you saying that you have an R coboundary expander given only if you have a spectral expander, or not quite?
Oh, yeah. So absolutely not. This not only am I not saying that, I'm saying that this is false, and the failure of this fact is the reason for much of the excitement in this field, because you cannot. Okay. Okay, so let me recall the main result in the graph case. Cheeger inequality for graph. I don't, so I can write it, okay, with so now it's k, it's the degree, mu 0 of x, and this is half mu 0 of x. So recall that for graphs we had this nice two-sided inequalities between the zero-dimensional spectral gap and the zero-dimensional Cheeger constant with respect to F2. And the interesting, sad, happy, exciting, whatever, pick your word, is that the Cheeger inequality fails in higher dimension. And if you think about it, even the people who know a lot about expanders, if you come to think about it, if I were to ask you to construct and prove something, construct something explicit and show that this is an expander, what you're going to do is to, usually, you're going to give me lower bound on the spectral gap. Because it's easier to analyze the spectrally, the spectrum of the adjacency operator of a graph. You won't compute explicitly the Cheeger constant. So without the Cheeger inequality, how can you prove that something is a high-dimensional expander in this definition? You don't have any spectral criteria.
Can you say a few words about the examples showing?
Yeah, I will give you one example, but I even go one step further in the story. So not only am I saying that, and what's important here, in particular, the important direction is not this inequality, it's this inequality. Spectral high-dimensional expanders does not imply F2 coboundary expander. high-dimensional expanders. So not every spectral high-dimensional expanders will be an F2 coboundary expander, but you can ask, well, what about the best spectral? Could they be? So one can guess that maybe Ramanujan complexes, one can guess that Ramanujan complexes are F2 coboundary expanders. And are Ramanujan complexes F2 coboundary expanders? And the answer is no. And let me tell you how easy it is to show that something is not an F2 coboundary expander. So coboundary expansion, F2 coboundary expansion, recall that expansion should be a strengthening of the connectivity property. Or F coboundary expansion in particular implies vanishing of cohomology with F coefficients. This is easy to see, right? I mean, if you have something in Zi which is not in Bi, this will be something positive, and here you have 0. So the coboundary will vanish. So if I want to give you an example of a spectral expander which is not an F2 coboundary expander, I only need to show you that the F2 cohomology does not vanish. And in dimension 1, this just means some condition on the abelianization of the group, the fundamental group. So this is let's call it a claim which appeared in the work of Kaufman, Kashdan, and Lubotsky. It's a simple construction. There exists a Ramanujan complex with such that its abelianization is not generated by powers of by squares, but this object is just the first group cohomology of the group gamma with respect to the field of two elements with the trivial coefficients, and this is equivalent. And I think I talked with somebody yesterday that this is also equivalent to the cohomology. So the cohomology of the group is equal to the cohomology of the quotient of the Bruhat-Tits building by the group, because the Bruhat-Tits building is a classifying space. And that's it. That's the example. So the Ramanujan property, which is a remarkable spectral property, doesn't really tell you enough about the group cohomology. So the second the group cohomology does not vanish, you're not a coboundary expander, and so we even have examples of Ramanujan complexes, the best spectral expander we can have, that violates this condition.
Excuse me?
Yes.
What is quotient?
Gamma divided by the commutator subgroup of gamma, and gamma square is the, these are all the squares of elements from gamma, and you might think, well, is this a group? Well, it doesn't matter because I quotient by the commutator. So this together will be a group.
So it's the largest abelian quotient and elementary 2 group.
Yes, exactly. So I should say, here's a question I find very interesting. So what's the torsion cohomology of quotient of Bruhat-Tits buildings? And you can restrict to congruent subgroups. It's not really a restriction because yeah, in many cases, the only possible co-compact lattices will be congruent subgroups. Okay, how much time do I have?
Like 16 minutes or so?
16 minutes, okay. So, but, so this was the bad news. The good news, so you see now why I have two talks, and one is called Spectral HD-expanders and Cohomological HD-expanders. These are two competing notions, they're not equivalent. Yes?
So the first one already fails, but does the second one already?
Yes, they fail in both directions, like F2 coboundary expansion do not imply spectral HD-expanders, but I don't have a conceptual example of the failure in the second direction. Okay, so now this is why I had the b, the little b there, hiding. So now I'm going to define a closely related notion called co-systolic expanders. And so I'll define the constant. So HZI of X, that's the minimum. It looks exactly the same. But now instead of running over all coboundaries, I'm going to run over all cocycles. And now this definition is guaranteed to be non-zero. Please recall that Zi is the kernel of delta F, And I also need to introduce another invariant, which comes from a systolic geometry. This is, by the way, this whole, many of these definitions are came from work of Gromov, who contribute a lot to geometric group theory, but geometry in general, and this notion of a cosystole, so this you can call it the cocycle expansion. And this, the cosystole, the size, it's a minimal size of the of a cocycle, which is not a coboundary, and then X is an epsilon, so it's an F, right here 2, I don't need a 2, F consystolic expander. If both of these constants are lower bounded by epsilon for all the interesting dimensions. So where is this definition came from, and why is this good for us? So I'll give you okay, so remark number one. So remark slash exercise for dimension one for graphs. What does this mean? So coboundary reduces to an actual expander. An epsilon consystolic expander graph is the following object: is a graph whose connected, so it satisfies two properties, whose connected component, so it doesn't have to be connected, are epsilon expanders. Each one of them is an epsilon expander on its own, and of size at least epsilon times the size of the entire graph. So its connected components are not too small, and each one of them is an expander on its own. So you see that this is a relaxation of the notion of a coboundary expander. In particular, I don't need connectivity. And there's another remark, which is really, really simple. So if the cohomology vanish, then there's absolutely no difference between the two constants.
Sorry, I can't read what you wrote. They're epsilon expanders, and then?
And?
Oh.
Yeah. So consystolic expanders are basically coboundary expanders, which I allow them to be disconnected. And the reason why this is, so you see now I kind of bypassed the problem in the counterexample that Alex provided in his book. And so this does not violate, this does not says that Ramanujan complexes are not consystolic expanders anymore. And in fact, not only oh, I forgot to do something very important. Like I gave you a definition, but I didn't give you an example, which is not good. So I told you that Ramanujan complexes are not always coboundary expander, but I didn't give you any definition of what are coboundary expanders. So let me just. So all of these examples are hard-earned. Complete complexes are, let's stick to F2. There are F, for any finite field, there are F2 coboundary expanders. There is a threshold phenomenon that random complexes above, with, let's say, with enough faces. So I refer to random complexes in the what is called the Lineal-Meshulam model, are also coboundary expanders. Spherical buildings also coboundary expanders. There's a beautiful paper by this was noted by Gromov, and there is a detailed proof by Lubotsky, Shachar Moses, and Linial-Meshulam. So we do have a few examples of coboundary expanders, but there is a problem. All of these examples are of what is called they have unbounded degree. The number of faces grows with the number, so the number of faces around each vertex grow with the number of vertices. And this is not so good because in the theory of expander graphs, usually one adds the requirement that a graph is an expander if it is Cheeger constant is bounded uniformly and it is sparse, bounded degree. Right? Yeah.
For spherical beings, you mean finite spherical beings?
Yes, finite. Yeah, all my complexes today are finite. I don't know anything about boundary expansion with infinite complexes.
So I don't understand the unbounded degree. What's unbounded?
So unbounded means that you can compare two things: the degree of any vertex, the number of faces containing a vertex, and the number of vertices. And what you want is this to be uniformly constant while the number of vertices grows to infinity. So a k-regular graph where k is fixed, it's a bounded degree. But if you look at the graph of lines versus planes in a projective, points versus line in a projective plane, you see that the degree is p plus 1 and the number of total vertices is 2 times p squared. Okay, so, and there was a question. Probably I'm doing it wrong. So there was a question, it's still an open question, raised by Gromov, Linial-Meshulam, not explicitly, but implicitly. So the whole notion of coboundary expanders came from the work of Linial-Meshulam from 2006 and Gromov's paper from 2010, both of whom, these are two lines of work, seminal works, in completely different directions. They care about random complexes. Gromov cared about certain geometric phenomena that probably won't have time to discuss, which had many different names in different fields in geometry, and convex geometry, like point selection, overlapping property, waist inequality, complicated fiber inequality. They're all different names describing the same phenomena. You want to measure how hard it is to map one space to another, and the way to measure it is to say, I'm going to run over all such maps, and I want to measure the size of the fiber. So this was Gromov's motivation. Linial-Meshulam wanted to study random high-dimensional complexes. Surprisingly, they both came across the same definition, coboundary expanders. So, two different motivations, the same definition. And the question is, are there, let's take to F2 coboundary expanders of bounded degree. This is still open even in dimension 2. For a while, Gromov started to believe that there shouldn't be any. And even it follows from his intuition that there shouldn't be even consistoric expanders. So it's not just the vanishing of cohomology that it's the problem, it's something else. But for lack of time, like the story, there is more to tell, but I can tell you what is important for us. It started and by really the crucial step was the work of Kaufman, Kasdan, and Brodsky. Actually, I should put here 3, and then it was extended by myself and Tali Kaufman for any dimension. And then there are some simplification and improvement of the constant, but the end result is that while coboundary expanders, it's slightly technical, there are F2 consistoric expanders in every of bounded degree of dimension d minus 1. There are F2 consistoric expanders of bounded degree of dimension d minus 1. What are these? Where did they came up with these expanders? So this is how you construct them. Take a d-dimensional finite quotient, or take a finite quotient of a d-dimensional Bruhat-Tits building. Use, so I'm not going to write it, but I'll tell you. Okay, so you take such a finite quotient and remove its d-dimensional faces and get a d minus 1 dimensional high dimensional expander Y. Okay, so there are two things. One, what goes into the proof? The proof is, in a sense, a local to global argument like Garland, but unlike Garland, it's not spectral. It can't be. We know that spectral can give us anything we want. But we are using the fact that for the Bruhat-Tits buildings have beautiful local structure. Their links are spherical buildings. And so we are using the fact that the links are coboundary expanders on their own. That's one. Another thing that we're using about Bruhat-Tits buildings is that their underlying graphs of all of their links and the full underlying graph of X are expanders. They're great expanders because of property T. So these two combines to prove this result. This result is, of course, a bit ugly, right? Because we would like X to be a high dimensional expanders, but we can only prove it for one dimension lower. If any of you have suggested...
And do we know that X is not, or is just we don't know if it is?
We don't know that it's not a consistoric expander. Like the proof is inherently, it needs an extra dimension. It's a proof informed by computer scientist intuition. So perhaps one needs some other ideas how to improve it.
For the previous question, it's still not excluded that for some suitable gamma, the Ramanujan complex this will also be coboundary.
So So you're saying whether there are some Ramanujan complexes that are coboundary expanders? Yes, absolutely. I should say that if you look in their paper, so remember I had this, let's look at the two-dimensional complex. So by this theorem, you get the consistolic expansion holds. So the only thing you need to do is to kill the cohomology. That's why my question from before, studying the cohomology of these finite quotients, is essentially the missing piece between proving coboundary expanders and not just consistolic expanders. And in dimension one, it's already, so a two-dimensional complex, if you want to kill the one-dimensional cohomology, you can use a little bit of group theory. The same equality of the first cohomology with the Berlinization of up to squares. This enables you, and it enables Alex under some conjectures from arithmetic group theory to show that there should be coboundary expanders, and they know which Ramanujan complexes should be the coboundary expanders. In higher dimension, I don't have any good criteria. So if there is some criteria to tell me when does the cohomology vanishes in dimension bigger than one, I'll be very interested in hearing about it. Currently, this question is still open, and at least the question of F2 consistolic expanders is solved. And I have 5 minutes, or I've passed 4 minutes after. Yeah. So okay. So like there are some beautiful applications that I didn't have time to show you. Maybe in the next conference. Okay, so thank you very much for your time.
Thanks, Shai, for yet another beautiful lecture. Are there questions?
What's the degree of this?
Yeah, I forgot to say. If you fix a Bruhat-Tits building and you take finite quotients, then this is bounded degree, right? Because the degree is governed by the building, and the building is locally finite. So you ask what's the specific degree of a Bruhat-Tits building, depending on the building. You should, I mean, there are some bounds you can use using the residue degree and the vibe group or the dimension. So you can take some uniform bounds, or you can be more precise and try to calculate it. I never calculate, but I know it's bounded degree, so it's good.
I have a question about the role of the fields Evan in this whole story. I mean, you did this like for finite fields, specifically F2, and then for the others, but you could take like any field, and how exactly does it influence what's happening with with these properties?
So as I mentioned before, there is the role of the field and also the role of the norm. So we should never forget that I use the Hamming norm, but you could use another norm. The role of the field, basically you can see one implication of when you pick a field, you basically automatically study the cohomology with coefficients in that field.
Sure.
So for instance, you can clearly the Cheeger constants of F2 and F3 cannot be approximate to one another if the cohomology vanishes in F2 and not in F3. So we know that the fields really matter even in under small changes. Other than that, I don't know how to say much. Yeah.
It doesn't make sense like to say to have such a property for FQ for a Q very large or something. Or...
I mean, it makes perfect sense. And if anything, if I want to kind of make sense of this theorem, it uses this is a combinatorial proof that would work for any finite field as long as you don't take the size of the field to grow with the size of the complexes. So I don't know the answer to the question what happens if you change the fields with the complexes. But the proof is combinatorial, and so it really is kind of, it doesn't see the field. But this theorem because the consistologist says nothing on the cohomology, and the cohomology clearly sees the field, and if you change the cohomology, I have no idea what happens for a single complex.
I would have one more question. Is this, in a sense, some canonical generalization of the expansion or because I mean the bound of the Cheeger constant, the spectral that fails in the higher dimension, right?
Mm-hmm.
So I mean, can I generalize it in another way such that this would work or something, or is this the canonical one?
Okay, so definitely not canonical. I'm claiming no canonicity here. Clearly, there is a dependence on, as I said, the norm. So different norms can give you different coboundary expansion parameters. And you're saying, what if I switch the definitions of the spectral gap and the definition of the coboundary expansion, and I do land on some Cheeger inequality? Well, in that case, I would ask you, so you don't use the refinement of the consistolic. I would ask you that if you did prove such an inequality, just to note that coboundary imply vanishing cohomology. So the spectral gap will imply vanishing of R cohomology, while the F coboundary will imply vanishing of F cohomology. And then I will try and think for a second of whether your inequality is correct, and if I can construct groups with vanishing R cohomology and non-vanishing F cohomology. So the Cheeger inequality, as it stands, it encapsulated not just a quantitative, but a qualitative topological consequence in it. So this is a problem with the Cheeger inequality in higher dimensions. And then it just so happens to be that in dimension 1, the R cohomology vanish and the F2 cohomology vanish if and only if the graph is connected. But in higher dimension, you don't have it anymore.
I knew that a few years ago with techniques from extremely combinatorics, people constructed like random complexes, but they didn't have bounded, degree.
Yeah.
And have any more steps been taken in this direction? Because for graph it works so well.
Yeah, that is a beautiful and frustrating problem in the field. Like it's not frustrating for me because I came from group theory and Bruhat-Tits buildings, and so the question of whether high-dimensional expanders exist received a complete answer using these rare objects, which are finite portions of Bruhat-Tits buildings. But one would ask whether there is a theory of random high-dimensional expanders of bounded degree. Like Linial-Meshulam is a beautiful theory of high-dimensional expanders of unbounded degree. I want some model that generates with positive probability a high-dimensional expanders and all the degrees to be constant. We don't have such a model. Not only that, there are, like they write it in their notes, both Gromov and Alex, both has intuition, Gromov from geometry and probability and Alex from group theory, to say that there shouldn't be a model that generates with bounded degree, let's say, consistolic expanders. This is an open problem, but they raise a conjecture, but the conjecture is stated imprecisely because what does it mean there is no random model? I take the pool of all finite portions of Bruhat-Tits buildings and I pick one from there. So, somebody should probably read Gromov seminal paper, and I can tell you where this conjecture is hidden. You can look at Alex's ICM talk. You can and listen to it. He had a different intuition coming from rigidity in group theory, and one should probably come up with a conjecture that one can try and disprove or prove. I don't know, but it's a problem. It's a serious problem.
No proof by contradiction.
Yeah.
Okay, so let's thank Shai again for all three of his